An AC circuit consists of an oscillating EMF which supplies an oscillating current to the circuit. The phase of the oscillation of the EMF may be different from the phase of the oscillation of the current supplied by the EMF. Similarly, the phases of the oscillations of the currents in different branches of the circuit may be different from one another. However, Ohm's law and Kirchhoff's laws still apply. We will express the oscillating EMF using an exponential with a complex number as the exponent. In this equation, omega denotes the angular frequency of oscillation of the EMF, and the subscript 0 denotes the amplitude of the oscillation. We will express the oscillating current using similar notation. As before, in this equation, omega denotes the angular frequency of oscillation of the current, and the subscript 0 denotes the amplitude of the oscillation. This is the equation for Ohm's law. It relates the current flowing through a component of an electric circuit to the change in electric potential across that component and the impedance of that component. Each term in this equation can be expressed as an exponential with a complex number in the exponent. Here are the impedances of the commonly encountered circuit components. Notice that the capacitor and the inductor both have an imaginary impedance. Imaginary numbers provide a simple means to denote phase. If an impedance has an imaginary component, the oscillations of the current supplied by the EMF are out of phase with the oscillations of the EMF. Let's consider the simple circuit shown in this figure that consists of only an oscillating EMF and an inductor. The total impedance of the circuit is simply the impedance of the inductor, which we can then use to determine the current in the circuit through Ohm's law. Substitution of the general equation for the oscillating EMF gives us the following expression. We can now rewrite this result by expressing the denominator in terms of an exponential. To achieve this, we will apply Euler's formula. Applying Euler's formula gives us the following result. Since the real portion of the impedance is 0, the angle in the exponent in the denominator is pi over 2. We can further simplify our equation by combining the two exponential terms. In this equation for the current, the amplitude of the oscillation of the current depends upon the amplitude of the oscillation of the EMF, the angular frequency of oscillation of the EMF, and the inductance of the inductor. The angular frequency of oscillation of the current is in the exponent of the exponential. The oscillation of the current supplied by the EMF to this circuit is pi over 2 radians out of phase with the oscillation of the EMF itself. This occurs because the impedance of the circuit attached to the EMF has an imaginary component. Recall that if an impedance has an imaginary component, the oscillations of the current supplied by the EMF are out of phase with the oscillations of the EMF. This is the equation for the average power supplied by the EMF to the circuit. It depends upon the amplitude of the oscillation of the current supplied by the EMF to the circuit, the amplitude of the oscillation of the EMF, and the real and imaginary components of the circuit's equivalent impedance. The number 2 in the denominator takes care of the oscillating nature of the EMF and the current. We don't need to include any exponential terms. For our simple circuit with only an inductor, the real portion of the impedance is 0. Therefore, the EMF in this circuit does not supply any power on average to the circuit. During half of the oscillation of the EMF supplies energy to the inductor. The inductor stores this energy as a magnetic field. During the other half of the oscillation of the EMF, the inductor supplies energy back to the EMF. Thus, the power supplied by the EMF oscillates between being positive, giving energy to the circuit, and negative, taking energy from the circuit. Therefore, the average power is 0. This is the equation for the average power dissipated by a resistor. It depends upon the amplitude of the oscillation of the current flowing through the resistor and the resistance of the resistor. The number 2 in the denominator takes care of the oscillating nature of the EMF and the current. We don't need to include any exponential terms. This circuit has only a resistor, and therefore only a real component to its impedance. The power supplied by the EMF is therefore the product of the amplitude of the oscillation of the current flowing in the circuit, the amplitude of the oscillation of the EMF, and a factor of 1/2 to take care of the oscillating nature of the current and the EMF. We can rewrite this expression using Ohm's law. The impedance of the circuit is simply the resistance of the resistor. We see that the average power supplied by the EMF to this circuit is equal to the average power dissipated by the resistor in this circuit. All power supplied by the EMF to an electric circuit is dissipated by the resistors in the circuit. In other words, the real part of the impedance is associated with the dissipation of power. The inductors and capacitors in an electric circuit store energy rather than dissipate it. In other words, the imaginary part of the impedance is associated with energy storage.